Hello and welcome back to Introduction to General Relativity. In the previous lecture, we discussed parallel transport from a slightly heuristic perspective, and I argued that there should be a correspondence between parallel transport operations and derivative type operators. The goal for today's lecture is to take these arguments and these ideas and build an abstract and intrinsic notion of a derivative type operator corresponding to a parallel transporter. An infinitesimal parallel transporter. These derivative type operators, we'll be giving them a name in this lecture. They'll be called covariant derivative operators. And our strategy in this lecture is to abstractly and intrinsically characterize those properties that we would like a covariant derivative operator to have. And then we're also going to call these things affine connections. And then we are going to explore what freedom we have in these derivative operators after we've listed a bunch of abstract properties that we would demand that any reasonable covariant derivative operator should have. So from now on, we're going to denote a derivative operator with like a nabla symbol. So our object of study today is a so-called covariant derivative operator. Denoted with this nabla symbol, and we also will probably call these affine connections. So that's our goal today, to characterize. So this is just the notation. To characterize these things abstractly and intrinsically. Now, some further notation. I'll probably use it here and there. You may as well get used to it. So let M be a manifold, and then we're going to denote by XM the space of smooth vector fields. On M. Okay, with that notation, with this notation in hand, I'm now going to tell you what a affine connection or a covariant derivative should do. What do we demand from it? Okay, here it is. We get the main definition now. So an affine connection delta. Well, first we're discussing a mathematical operator, so we should say what it acts on and what it produces. Is a map delta going from smooth vector fields cross smooth vector fields. So it takes two smooth vector field entries and produces one smooth vector field output. But what we will do is we will immediately extend domain of definition because it turns out that the axioms that I'm going to list will just be easiest to phrase in a wider setting, namely to the setting where delta takes as an argument one smooth vector field, but as its second argument it just takes an arbitrary tensor field of type KL and produces an arbitrary tensor of type KL. So basically everything I write in the following list of abstract requirements of our tensor, about covariant derivative or affine connection, can immediately be extended to tensor fields, where the second argument is tensor fields. Alright, so what are some requirements that we demand of our abstract covariant derivative operator? Well, there's a couple of really very simple zeroth requirements that aren't listed in Wald's textbook, but are required if you want to make sense of this thing as a linear map. These requirements are as follows. So let x, y be vector fields, and z just a tensor field. So it could itself be a vector field, right? Then we demand that this covariant derivative operator, you've got to think of a covariant derivative as kind of like a directional derivative operator. If you take a directional derivative in directions x plus y of z, then that's just going to be, it's got to be the same as doing it with respect to x on z, y on z. And then there's a second zeroth requirement, namely for all smooth functions f, we are going to also demand that delta of f times x, which is also a smooth vector field, on y is f delta x on y. So x here is a smooth vector field and y is a tensor field. So we really do need these zeroth and zero primed conditions because we want to deploy abstract index notation as soon as possible to talk about this thing or the way it acts on things, and for that we're actually going to implicitly need these linearity in the first argument type properties. So let's now come to the first major requirement, namely linearity. So delta x of a plus b had better be the same as delta x of a plus delta x of b. That any decent derivative operator is linear in this sense, and in this case a and b are tensors and x is a vector. Let's move that down and write that clearly here. We demand that. Now, because of 0 and 0 prime, we're able to express this requirement in abstract index notation. So we can actually write this out as follows. Namely, by noting that the abstract, that delta x is, think of delta x as a thing that eats tensor and produces a tensor. So itself, delta x should be a tensor of a different type. And we're going to express this in abstract index notation as follows. We're going to introduce the following notation to denote the covariant derivative operator with respect to abstract index notation. So whenever you see xa contracted with delta a, you know that means that we're talking about delta x. And so this, with respect to this abstract index notation, we can write this linearity condition as follows, right? We can write it as delta c of a1 through to ak, b1 through to bl, plus ba1 through to ak, b1 through to bl is equal to their linear combinations. Okay, so that's the linearity property of the covariant derivative operator expressed in abstract index notation. You can see that these two things are equivalent according to this notation, whereby delta x defines this thing delta a. 2, the second thing you want any decent derivative operator to satisfy is the Leibniz property, or Leibniz rule. So for all a and b, now they're in different places, tensor KL, so all Ka tensor fields of type KL and all B tensor fields of type K prime L prime, we want that delta x applied to A outer product B is the same as delta x applied to A outer product B plus A tensor delta x B. So actually I'll just highlight these various requirements as we go, just so you can see them in the notes later. A bit better in the notes than later. Here's the first 0th requirements. Establish the linearity in the first argument. The first requirement establishes linearity in the second argument. And the second criteria here that we demand of a good, decent, covariant derivative operator is that it obeys a Leibniz property. And we can also write that in abstract index notation, or represent this in abstract index notation as follows. So delta C A1 through to AK, B1 through to BL, outer product, right, which is just represented by concatenation in abstract index notation. That's equal to doing the derivative operator on the first argument and concatenating with the second tensor field, plus doing concatenating the first tensor field and concatenating it with the second. Oh, I wrote C here. That's probably a bit poor choice. Delta E. Okay, so that's the Leibniz rule in abstract index notation. There's another condition that we had better demand. You almost wouldn't notice it, but you have to demand it. It is a condition. Commutativity with contraction. So if you covariant derivative something and then contract versus contract and then covariant derivative, it better be the same thing. So in non-abstract index notation, so if I contract the jth and the j primeth entries of a tensor field A, I better get the same as if I contracted those entries of the tensor field after the covariant derivative. But because we've introduced a new entry, I'm going to write it like so. That's commutativity with contraction. It's semi-obvious if you've got linearity in the second argument already. And we can write that out in abstract index notation. How do we represent that in the AIN? Well, we're going to use we'll represent it so. Okay. Now the fourth condition that we want just tells us that if we apply our derivative, our covariant derivative, to something where there is a unique notion of derivative, namely on scalar fields, on smooth vector on smooth scalar functions, then it better do the same thing. You know, we haven't reinvented the wheel, so reduction to vector fields on scalar functions. We know that directional derivatives are in one-to-one correspondence with vector fields when applied to scalar functions, so our delta better be doing that, or better be consistent with that. So if f is a smooth function on the manifold n, then it better be the case that if I do the covariant derivative in the direction of the vector field x, on f, that's really just the same as applying the vector field to the scalar function. So it's okay. This operator does the same thing when restricted to scalar functions. And in abstract index notation, we denote that as follows. Finally, the fifth condition is not necessary, but we do assume it in many parts of general relativity. We demand that the covariant derivative operator is so-called torsion-free, which means that for all smooth functions f in M, wait on, I'll do it the other way around first, which says the following object, which is a tensor, is 0. So this condition is not necessary, but is very convenient for many parts of general relativity to assume. So if we take the covariant derivative in the direction x of a vector field y and subtract from it the covariant derivative of x in the direction y, and then subtract from that the commutator of these two things, then we should get 0. This is a bit sort of opaque, the interpretation of this, but in abstract index notation, you can show that this condition is equivalent to the following, which is somehow has a much more intuitive meaning, namely that for all smooth scalar functions on the manifold M, if you take the covariant derivative in direction A and then B, that it should be the same as doing it in direction B then A on a scalar function, smooth scalar function F. So it's much more easy to understand criterion. So these are the 5 plus 2 conditions that you might demand from a covariant derivative operator. Are they all independent? There's some redundancy in these axioms, but that's okay. I mean, we're not out for the most economical description of the requirements of a covariant derivative. We just want to have a laundry list of all the properties that are required, that we would require. We don't care if there's some interdependencies as long as they're all consistent. Now, there's some simple consequences of these conditions that we can immediately deduce. So, for example, if you have two vector fields x and y and a scalar function f, then if you take the covariant derivative in the direction x of the scalar function times by y, then we can apply Leibniz and the reduction to vector fields on scalars to learn immediately that object is also a vector field and can be expressed in the following fashion. So that's an interesting simple consequence just of Leibniz and the reduction to vector fields on scalar functions. And the second one is also kind of an interesting way to compute the commutator of two smooth vector fields. So if you have two smooth vector fields v and w, you can naturally form their commutator, as we described quite a few lectures ago now. As how do you do it? Well, you just do the vector field once, then twice, and then do it in the opposite order. It should be a minus sign, almost certainly. And well, there's something rather interesting, right? Namely that we can, W of f is a vector field applied to a scalar function, but we could also interpret that as the covariant derivative applied to f contracted with W. That comes immediately from condition 4, right? Condition 4 says that. And then we can also subsequently apply the covariant derivative in the other directions. Now, why is that interesting? Well, we can now apply Leibniz property. So we've got the covariant derivative here with respect to v and then w. We can apply Leibniz onto these objects here inside the bracket, and we apply it to the first argument, which is a vector field, and we apply it to the second argument, which is a co-vector field, using just the Leibniz property, and we obtain the following next line. So we apply the covariant derivative just to the vector field w, and leave the covector field delta bf alone. Then we apply it to the second part of the bracket here, so to obtain delta a vb delta b f, and then we do the same again. Oops. Wait, no. So this second term here that I've just written out is using Leibniz on this second term in the commutator. And then we've got two more terms that we have to add in. So we've got VA WB delta A delta BF. That's Leibniz on the second term. And VA WB delta B delta AF. But according to torsion freeness, these two things here are 0, right? So they vanish. They don't vanish separately, but their difference vanishes. So we actually can get a formula for the vector field, this commutator vector field. Can interpret this vector field as the following tensor. And the following vector field. That's pretty neat. Now, what we've done is just written down a list of, a wish list, right? This is just a wish list. We would love a covariant derivative operator to do this, and this. Look, we could also ask that the covariant derivative operator go shopping for us. But it's all very well to make a laundry list of things that you would like. The problem is, when you make a long list of things like that, you may not have anything that exists that satisfies such a long list. Or you might have too many things that obey the list of axioms. In our case, it turns out there's more than one derivative operator which obeys these conditions. That's fine. But now our job is to understand this arbitrariness and connect it to geometry. So there's many derivative operators obeying these conditions. I got to at least prove to you one exists, right? Otherwise you might disbelieve me that anything obeys these conditions. Well, here's an example. Namely, is the ordinary derivative operator in some chart. And how do we define it? Well, it's defined as follows. We have to pick a chart, right? This is the first part. So this is coordinate dependent. I'm going to present to you a derivative operator that is defined with respect to a coordinate system. That's okay, right? But you might worry that there's no coordinate independent way to work with derivative operators. I'll subsequently argue that's not the case. So it's defined as follows. Let psi be a chart and T a tensor of type KL with components now, right? It's we're going to represent this tensor in this coordinate system, T mu. I'm using Greek letters here to indicate that. So in the coordinate basis, it has those components, and delta acts via the following. So suppose we encounter this abstract index notation here, well, we interpret that abstract notation in the coord basis, the coordinate basis, as this defined by psi, as this tensor field, where we've just taken the derivative with respect, the partial derivative with respect to the sigma component of these functions t, these components in the coordinate basis. So this is, obviously this isn't, it's not defined everywhere. It's only defined in the chart sigma, psi. But it at least establishes that with respect to one chart, there exists at least one derivative operator obeying all those conditions. You can, just check, you can check yourself that delta obeys these conditions, obeys 0 through 5. Okay, that's an exercise for you. So now let's understand the freedom in derivative operators. It looks like we've got one. Two things could happen. Maybe that's the unique derivative operator, or there's more than one, and we want to understand the arbitrariness in defining a derivative operator. Of course, the answer is that there's more than one. So let's understand the freedom in defining derivative operators. So we're going to suppose that we have two different derivative operators. That obey these conditions. So suppose delta and delta twiddle are two covariant derivative operators obeying 0 through 5. And we're going to understand the freedom of definition that we have after applying all these conditions that a derivative operator has to obey. What's left over? What degrees of freedom are left over? So let's start with its action on scalar functions. So as a map on scalar functions, smooth functions on the manifold, we learned that the difference between these two operators applied to a scalar function vanishes. Right? That's just a consequence of condition 4. So there's no freedom. On scalar functions, as an operator on smooth scalar functions on a manifold, there's no difference between two different derivative operators. They're the same thing. They act the same way. But of course, we've defined derivative operators to accept an arbitrary argument of tensor type KL. We're going to slowly build up and understand the action of the difference on as we enlarge the domain of definition on which these things act. So suppose we act our difference now on a covector, on a tensor of type 0, 1. Well, what can we say? Well, it accepts a covector, the difference of these two, and it produces a tensor of type 0, 2. That's just the definition. So delta A, remember, is the abstract index notation. Now let f be a smooth function, scalar function, and omega is an arbitrary covector, dual vector. Then one thing we can do is we can multiply scalars by dual vectors and get other dual vectors. And now we're gonna learn something from this Leibniz property. So this is the key strategy to determining this difference on and understanding the freedom of definition in covariant derivative operators is this following trick. So form the difference and apply it to our scalar, and then simply do Leibniz, right? And you'll learn that this difference commutes with f, right? You can push the difference of these two derivative operators, you can move it backwards and forwards past this any arbitrary smooth function f. So this is, via the Leibniz property and condition 4. Now that turns out to be an extraordinarily restrictive condition on the behavior of the difference of these two derivative operators. And in fact, we're going to learn that this completely determines their difference except at the point P itself. So this condition star that I've highlighted here, condition star implies that delta A twiddle on omega B minus delta A on omega B only depends on the dual vector at P itself and nowhere else, not even on the neighborhood around the point P. Now this is weird, right? This is not what you might initially expect. If you have a derivative operator and you apply it to a function, then it depends on the first order neighborhood around that function at the point P. So we're saying that the difference of two derivative operators, while itself being a derivative operator, somehow doesn't depend on even the first order neighborhood of the argument around the point P. And how are we going to do this? How are we going to claim? How am I going to demonstrate that that statement is correct? Well, so the strategy will be as follows. What we're going to do is we're going to let omega b prime be another dual vector field which agrees with omega b at a point P. So define omega b prime to be just some other dual vector field that when you look at the point P is absolutely equal to omega b, but can be different, arbitrarily different elsewhere. And then we claim, or we're going to argue, we will argue that the difference of these derivative operators applied to these various omegas are in fact equal. Okay, not obvious, but we will prove that. We will argue this. Now, the way to arguing this is to use this exercise that we had from this Taylor expansion exercise that we considered, I believe, in lecture 3 already. So one can find exercise smooth functions f. Okay, yeah, right. There's some potential for confusion with this round bracket notation. Let's just say f subscript alpha, which vanish at P, and a smooth dual vectors mu b, and I'm going to have to use a funny notation for these because I don't want you to think that these are tensors of type 1, 1. No, they're just a list of dual vector fields such that when you look at the difference between omega b, remember omega b is our dual vector field that agrees with omega b prime is our dual vector field that agrees with omega b at the point P. Well, around the point P, we learn that you can represent this difference of dual vector fields as a linear combination of dual vector fields where these coefficient functions here vanish at point P. It should be intuitively okay, clear. It's kind of like a Taylor series to order 1, and you just use that calculus result that we proved. We didn't prove that we exploited in arguing that the coordinate derivatives are a basis for tangent space. So I think that was lecture 3. So we have this representation here. this key representation here. So whenever you have a pair of dual vector fields that agree at a point, then you can look at their difference and it will be expandable in this way. And so f of alpha at p equals 0. And now we're going to apply our covariant difference of covariant derivative operators. And we're going to learn something interesting as a consequence of that representation. So we exploit the fact that that difference commutes past scalar functions, which we established as an exercise just above. And then we see that this has to equal 0 at p. Why? Because these coefficient functions vanish at p. It's pretty amazing. Hence, we've learned that delta A twiddle minus delta A applied to our alternative dual vector field omega b prime is equal to delta A twiddle minus delta A applied to omega b at p for all omega b primes that are equal to omega b at p. So the difference here doesn't depend on omega b out away from the point p. It only depends, the difference of these derivative operators applied to some dual vector field only depends on the value of the dual vector field at the point p. And that's pretty amazing, right? Because what that tells us is that because we know already that delta A twiddle minus delta A is a linear map of tensors, it's a map of tensors that doesn't involve the neighborhood around the tensor. It's a map of tensors at the point P. So you can interpret this as a map of tensors at each point P. And it's not, okay, it's a map of tensors of type 0, 1 at the point P. Nothing more. No, it doesn't depend on any extra data. And it's a linear map because of the linearity condition. And so what is it? It's a linear map. So defining this difference, we'll call it C for the moment. C takes a dual vector at point P and gives us a element of VP star tensor VP star. Right? Because delta takes a dual vector and produces an object, this object here, and this object has, in abstract index notation, 2 indices at the bottom, so it's a tensor of type 0, 2. So 2 tensors of type 0, 2. So C is a map, a linear map of vector spaces like so. Now remember, you can do this duality trick where you, by duality, remember VP star star is equivalent to VP, you can interpret we can interpret C in a different way as a map that goes from as a map from VP star tensor VP to the reals, or as an element of the tensor product vector space VP tensor VP star. Now we're going to write CABC for its, or CCAB, sorry, for the abstract index notation of C. So C is just a tensor field by no derivative left anymore. The difference in two derivative operators is just a tensor field. It's not a, it's not doesn't have any further action as a derivative operator. So that's pretty cool. That's really striking observation about the difference of two derivative operators. And just expressing this information we've gained in one equation, we learn already how we've completely understood the freedom in defining these covariant derivative operators, because we know that if we have two covariant derivative operators, then the covariant derivative of the first type of some dual vector field is the covariant derivative of the second type minus some tensor field applied to that dual vector. So let's now we're going to learn even more dramatically how that data there is enough to specify delta on all tensor fields. We'll learn it in a sec, but before we do that, we're just going to notice something about the symmetry. So suppose that we're assuming that our derivative operators are torsion free, then that means that on scalars, on the following object is symmetric, right? Delta A, delta B equals delta A, delta B, twiddle F minus C, CAB. I'm just using the equation above, but we notice that this is symmetric, that's torsion freeness, but also by assumption, because delta twiddle obeys equation 5, that's symmetric, so that implies that CAB is also symmetric. The only way this can happen is if CAB is also symmetric. Okay, so what we've seen so far is that we've abstractly characterized things that we call covariant derivative operators, and then we've said, what if we have two different coordinate covariant derivative operators? How different can they really be? And then we've applied the various axioms that we demand, or conditions we demand, of a covariant derivative operator, and we see that really the difference of two covariant derivative operators on a dual vector can't be that strange. In fact, it's just the difference is just a ordinary old tensor field of type 1, 2 applied to the vector field, the dual vector field omega c itself. Now, the further amazing consequence, once we've established this, is that actually that's all the information we need to completely specify delta on all tensor fields. So the Leibniz property and 4 now actually determines this difference, and thereby the freedom of covariant derivatives on all tensors. I'm not going to show it to you for all tensors. It's just an inductive argument. I'm just going to show you how this formula in the yellow box, the red box yellow formula here, determines the derivative operator on all vector fields, and then you'll see the trick. Once you've seen the trick, you can generalize it. So let omega be a dual vector field, and T a vector field. My other notation for that is xm. So what do we know? We know, according to abstract index notation, that omega a t is the contraction of omega and t, and is therefore a smooth function. Now 4 says that the derivative operators commute with contractions, right? So we already learned this. Four already tells us that the difference applied to a scalar function is 0. Sorry, 4 isn't commuting with, yeah it is. No, 4 is reduction to scalar functions. I apologize. I got confused here. So condition 4 is that a derivative operator reduces to a vector field on a scalar function. condition 3 is commutativity with contraction, and that's what we're about to use now. So now we use Leibniz and 3. And we learn that the following expression vanishes. Now we substitute the definition of C. And what are we going to learn? Well, we find that TB C CAB omega C plus omega B, and we don't substitute in the second one actually. We can't. So because this thing we don't even know what that is yet, but we definitely know what it is in the first term of this expression. So, but what we have learned is, well, we know what that is. This first term here, that's just a contraction of some tensors, some tensor fields. And this is almost the thing that we want, and then we use the linearity of these covariant derivative operators, and we rearrange this expression here and factor out omega b. To learn so we're just factoring out omega b here. This expression vanishes. Or what's another way of writing this? Well, another way of writing this is it tells us how these derivative operators act on arbitrary vector fields in terms of data that we already have. So this trick can be applied inductively to find out now how delta and delta twiddle act on an arbitrary tensor field, and namely what's the difference between these two actions. So as an exercise, I mean, it's not such a hard exercise now that you've seen the trick. Just a bit tedious and you have to get down there and do it. We learn that the action of a covariant derivative operator on a tensor of type KL is already determined once you know this tensor field C. And what you get is this expression here. So you get that the action of a derivative operator on an arbitrary tensor field is the same as the other derivative operator, plus all the contracting with the C tensor in all the places you can contract it one by one, and summing up the answer. So in other words, the action of delta A twiddle minus delta A on arbitrary tensor fields of type KL is determined already by the data of a tensor field of type 1, 2. And the converse is also true, right? You know, converse. If someone hands you, or if you decide to hand me, a tensor field of type CAB, then this determines a derivative operator as above. I've just realized something that I have to correct. I'll do that in a second. Converse. So given this field of numbers here, functions here, and a derivative operator, delta A, twiddle, then defining delta A defined by delta A twiddle, by star star, is also a derivative operator. And now I realized there's something that is slightly incorrect potentially in what I've been writing. So I've been saying that this object here, C, is a tensor. That was not quite correct. Not a tensor in the sense of general relativity. And I knew this confusion was going to happen at some point here. And I did it. I apologize. I made this mistake. So CAB does not, this is an annoying part of perhaps the abstract index notation and the terminology surrounding differential geometry. CCAB is a list of functions, or you can think of it alternatively as an element of this tensor product vector space here for all points P in the manifold. Very, very important warning, CCAB does not transform as a tensor of type 1, 2. It actually obeys a different transformation law. So it doesn't transform as a tensor field of type 1, 2 under change of coordinates. And so earlier I think I inadvertently implied that it did, so I better go through and correct the notes. So we'll go back slowly. So CCAB is a list of functions, or it's a element of this vector space at each point P in the manifold. Okay, so far this is okay, what I've written here. Yeah, I think I may have gotten away with it. I don't think I actually wrote CCAB is a tensor of type 1, 2 at any point. No, looks okay. So, but I'll go through these notes here and stress this point one more time, because I can anticipate that this is confusing. So delta twiddle minus delta A is a thing. It's a map of tensors of type 1, 0, 1 at P. This does not imply that C, that I've defined down here, is a tensor field. It's a linear map of tensors at each point P in the manifold. So this is all true here. By duality, C can be interpreted as a map from V star tensor VP to R, or as an element of VP tensor VP star at all points in the manifold. If you were to change your coordinate basis, then CAB transforms in a way that's not a tensor field. And that's where one should be a little bit cautious with this abstract index notation, because it sort of implies that CCAB is a tensor field of type 1, 2. So I'll put it in red here, but CCAB is warning, is not a tensor field. Okay? Field is the operative word here, of type T1, 2. Why not? Because if you were to change coordinate bases and recalculate CCAB, then you get something that is not what you would expect from the tensor transformation law. It transforms in a way, just not. It does not transform as a tensor field of type T1, 2. In fact, you get some extra terms. All right, there's a very important example of the application of these observations, is namely when delta A twiddle is the ordinary derivative operator that I introduced above. So in this case, we just use a different notation. And for these C coefficients functions. And we call them Christoffel symbols. And we just write for the derivative operator, we use the following notation, which in coordinates, so if you go to a coordinate basis, you can then write the action of this derivative operator, covariant derivative, on the vector field as such. Oops. Okay, that's it for today. We've introduced abstractly the list of requirements that we would demand from any covariant derivative operator that we attach or associate with parallel transport on a differentiable manifold. In the next lecture, we're going to see how the data of the metric on a manifold is enough to completely uniquely isolate one particular special derivative operator, and that's the one that will play a key role in the formulation of general relativity. But that's it for today. Thank you very much, and goodbye.